Good morning, everyone. Welcome to day 2 of the 12th Annual Canadian Water Summit. We've got a full day ahead of us. There's going to be a lot of chances for breaks and opportunities, so feel free to get reacquainted or acquainted with the platform and message attendees and the community board throughout the day. We're very excited to present to you our session on emerging contaminants in wastewater. So my name is Alan Shapiro. I'm the director of the WaterNext Network, which is a pan-Canada network driven by Foresight Cleantech Accelerator, supporting acceleration and adoption of Canadian water innovation. I'm based in Vancouver, so apologies, I'm still starting my day. And before we kick it off, I do want to acknowledge that I'm joining from the traditional unceded territories of the Musqueam, Squamish, and Tsleil-Waututh peoples in Vancouver. Especially as we talk about water challenges, I think it's so important to remember that the pressing challenges facing First Nations communities across the country are still around clean drinking water. Now, the list of contaminants in our wastewater continues to get longer. We have these contaminants of emerging concern that include pharmaceuticals, personal care products, nanoparticles, flame retardants. You might have remembered a few years ago that BPA was the conversation of the day when we were pulling plastic water bottles from shelves. More recently, PFAS is something that's very high on many of our radars. And then I know with the work that Professor Ormeci has been doing, COVID-19 obviously is something that over the last year has really pulled together the wastewater community to design new analytical methods. So some of these contaminants are brand new, some of these contaminants are established, and we're just starting to wrap our heads around the risks in research now. But many of these compounds are not easily removed from water with conventional treatment techniques, which poses challenges for governments, for operators, and for many of the folks in the community joining us today. So I'm looking forward to moderating this discussion with Professor Stephen Liss from Ryerson University and Professor Banu Ormeci from Carleton University. And I'm going to hand it over first to Professor Liss to walk us through some of your own work, as well as some background on emerging contaminants from your perspective.
Great. So thank you very much, Alan, and delighted to be here to join you and to join Banu in this discussion. And I'll just take a moment just to share my screen. There we go. Hopefully people can see the screen in front of you that I'm sharing. So let me just begin by saying that the development and implementation of risk management plans for water based on quality requirements is limited by what is considered safe. In the context of human health, safe water contains negligible, if any, levels of harmful contaminants such as pathogenic bacteria, viruses, or protozoa, cancer-causing chemicals, and any other acutely toxic substances. Of course, there's potential in emerging contaminants such as personal care products, pharmaceuticals, and antibiotic resistant microbes, amongst many of the things that Alan indicated in his opening remarks. It may cause less acute illness, but pose significant challenges to populations, and particularly impacting those who are frail, elderly, and children quite differently, making them difficult to address and include in risk management plans. But as this slide illustrates in two pieces that I've penned for the conversation rising from acute crises, these draw attention to the need for multi-level risk management plans that are preventive rather than reactive and address the greatest risks and draw on experiences and adequately invest resources for risk mitigation. In this regard, what the Flint, Michigan crisis revealed was that, in fact, when the crisis is over, as the headlines in 2017 in Canada for the situation, including the mercury release in 1962 through 1970 and the Wabigoon English River system going to mercury contamination. This is a considerable number of years ago, decades ago. Grassy Narrows and Wapasimung, and each about 100 kilometers from Kenora near the Ontario-Manitoba border. And to this day, residual mercury in the water supply continuously impacts that community with long and far-reaching health impacts. So crises are really never over. And even when there are solutions, as was revealed in the issue with regards to disinfection byproducts in Newfoundland water supplies brought about by chlorine interacting with high organic content in water. And there are solutions for these. There are governance and decision-making authorities sometimes limit the ability to address water when the solutions are very much in front of us. So many of these things draw my interest to the issues of water. And my background, just as a way of understanding this, and this is a crowded slide with lots of nice pretty images and some evidence of some of the publications that we have generated in recent years, particularly on microbial structures and biological processes and water and wastewater systems, natural and engineered, illustrate the important power and but also the challenges with respect to the biology in these systems and the rising of microbial pathogens and emerging pathogens as a point of concern as well. And so I look at this from a lens as a microbiologist by background, but with obviously an orientation to environmental sciences, environmental engineering in the various academic positions I've held at Ryerson, at University of Guelph, and at Queen's University over the years. But look at microbial interfaces and engineered natural environmental systems. So we look at all sorts of scales, from bench scale like laboratory experiments to sampling and studying full scale and natural environmental systems, to looking at the various components within these systems, particularly around the biological processes and the microbial structures that lends itself to the efficiency and effectiveness of our treatment systems, but also our management of natural environmental systems as well. And my focus, it really has turned its attention to many aspects of the fate of contaminants and pathogens in these systems, and particularly on antibiotic resistance genes, which we've written extensively over the last couple of years. So that's the lens I come from and how I look at the problems, but also drawing back to some of the crises, as I indicated in the opening slide. So let's consider antibiotic resistant genes as a contaminative emerging concern. A number of years ago, when we were beginning to write on the subject of ARGs as contaminants of emerging concern, there was a lot of pushback as to whether or not ARGs were contaminants. And antibiotics might be seen to be that way, as defined by Moratti in 1984, that indicates a contaminant is a chemical compound that are released by human activity. And certainly antibiotics that enter into the system or discharged as they're excreted from humans taking antibiotics or being flushed down the toilet, as we know it occurs. Antibiotics do enter our wastewater systems. But more importantly, antibiotic resistant genes have been seen to be more important and perhaps more problematic with respect to the transfer across bacterial communities and as an impact of antibiotic pollution and co-selection of antibiotic resistant genes that exist with other contaminants like heavy metals that further exacerbate the potential and problems of emergence of antibiotic resistance through hotspots and in reservoirs. And as the two figures in these slides illustrate, there's a great deal of intersections between the various hotspots and reservoirs, from the clinical to the gastrointestinal tract of humans, to agricultural and farming practices, and to our water systems that and the exchanges between these that create a real mixing pot for antibiotics and antibiotic resistance genes in particular. And these and wastewater treatment systems in particular are very suited to the transfer of antibiotic resistant genes across the microbial community, bacterial community in particular. So the environments are connected through water and transformation in marine water and sediment microcosms is well established. There's a strong correlation between the presence of antibiotic resistant genes and composition of bacterial communities. And of course, we know that certain co-selection and relationships with other contaminants can exacerbate the problem as well. So when you think about what a contaminative emerging concern is, as defined by the US Geological Survey, it was quite revealing as to the challenges in understanding how ARGs might be a contaminative emerging concern. It's any synthetic or naturally occurring chemical or that is generated by microorganisms that is not commonly monitored in the environment, but has the potential to enter the environment and cause known or suspected ecological and human health effects. And so I know we will probably return back to the subject of the definition of an emerging contaminant or contaminant emerging concern, but clearly antibiotic resistant genes fall squarely into this definition. What I want to just illustrate, and I know Banu will speak a little bit about this as well. I mean, our labs have been very involved through Ryerson Urban Water, led by Claire Oswald and Kim Gilbride, including my lab and others across the university in screening our wastewater systems including sewers and outlets from large facilities like long-term care facilities to understand the risks associated with SARS-CoV-2 and the emergence of SARS-CoV-2 infection, given that the virus is discharged and excreted and passed into the sewage system and could be a telltale sign of emergence of outbreaks or new waves of infection. The point of this slide is to illustrate how our labs in Ontario and across Canada have been all mobilized effectively to take advantage of the infrastructure and the expertise in water, wastewater, and our backgrounds in molecular sciences and microbiological sciences to implement a surveillance program and working with the provincial government. And the second message around this is around methodology. And this slide is really to illustrate that from this point of sampling from the sewer system, we have the methods in place that have been adapted and evolved for many years working in molecular sciences and molecular ecology to have tools in hand to effectively extract and to detect the respective genetic material to identify CoV-2 in these wastewaters with a great deal of sensitivity and low concentrations. What I want to further indicate is that there is a significant opportunity to create high throughput with respect to surveillance and managing high numbers of samples that come in, and in terms of generating real-time information on this. So our laboratories and the methodologies that have evolved apply also equally to the chemical analysis of emerging contaminants, be it antibiotics, drugs, pharmaceuticals, personal care products, to the microbiological contaminants and microorganisms of interest, and including Legionella as well, which is of course a microbial contaminant in our water systems, particularly in the built environment and in reservoirs that can pose risk as well. But we have the methodology and tools to use this and surveil. So it begs the question as to the extent of surveillance that can be incorporated and should be incorporated looking forward into the future. And so we're not short of methods and ability to detect and monitor our water and wastewater systems for emerging contaminants. But the question is the leadership and to address the acute crises, the failures, to address the crisis, and to invest in programs and resources that incorporate broader environmental protection requirements, community involvement, education, and research to better address contemporary water issues and prevent future water crises. And that includes also treatment options as well. But we have the ability to surveil and to monitor and to convey confidence that I think our communities and people's want to understand that they are drinking safe, clean, and healthy water. Thank you very much.
Thank you very much, Stephen. I bring an inorganic perspective from the work that I've done before. So it's so interesting to look at just how broad the range of contaminants is, and then the methodologies and processes that evolve from that. I also want to ask the audience, I know we've had some questions trickling in already, which is great. Before we hand it over to Professor Ormeci, if you have questions throughout, feel free to post them in the chat, and then we'll get to them in our discussion. So Professor Ormeci, handing it over to you. And you're currently muted.
Yes, can you please confirm if you can see my slides?
Yes, that's perfect. Okay,
perfect. So I would like to give a quick overview of emerging contaminants in wastewater, but also sludge. Sludge is important because wastewater discharges are to surface waters, but sludge is land applied. So if there are emerging contaminants in wastewater, there is also the potential to contaminate not only aquatic ecosystems as well as terrestrial ecosystems as well. Okay, so what is an emerging contaminant? What is not emerging contaminant? The definition changes. The types of contaminants that we focus on over the years also change. But right now, these are some of the hottest emerging contaminants. So persistent chemicals, there is a whole wide range of them. Thousands of these chemicals are unfortunately used and discharged to the environment. But the main issue is obviously they're persistent to environmental degradation, but they're also persistent to biological or chemical degradation during wastewater treatment. And another concern is some of these chemicals can accumulate in the environment, and worse, some of them can bioaccumulate, which is different. And so that adds additional concerns. Emerging pathogens, we typically focus on E. coli, total coliform, but remember that those are indicator microorganisms. They're not really pathogens, and they are one of the easiest to kill compared to other pathogens. And there's a whole range of viruses, bacteria, and protozoa that can be very harmful to public health, which is in wastewater. Now, SARS-CoV-2 is not necessarily a waterborne pathogen, but it does end up in wastewater, and as a result, it ends up in water environments. And I also work on monitoring SARS-CoV-2 in wastewater. But so even sometimes the pathogen itself may not be waterborne, that can still be a concern for us. Antibiotic resistance, as Stephen mentioned, this is also important. I know, a couple of years ago, people would look at this idea as a far-fetched, creating superbugs. But after SARS-CoV-2, I think that there is more of a concern, the possibility of gene transfer, antibiotic resistant gene transfer. And remember that gene transfer can be vertically from mother cell to daughter cell, but it can also happen horizontally. So wastewater treatment plants, they're really the ideal breeding grounds for this to happen. Nanoparticles, they are used in the industry, in manufacturing, in clothing industry. As a result, they end up in wastewater. Silver nanoparticles are the most common ones, but there's a whole range of other metallic nanoparticles, which can be quite toxic. And microplastics is the latest one. So this has been already a hot topic in Europe already for some time, but now in Canada, we're also talking about microplastics, and not also microplastics, but sure enough, there's also something called nanoplastics. And remember that microplastics, they do not decompose, they do not biologically degrade. They are in the environment for hundreds of years, 700, 800 years. Some types of plastics can stay around for thousands of years. And so this is a concern because they're not gonna disappear, they're not gonna biodegrade. What can we do? Action items, it's very, very important to be proactive rather than being reactive. And as the water industry, wastewater industry, we are usually reactive, something happens, and then we try to react to that. But taking proactive steps such as banning or phasing out some of these really persistent chemicals that just should not be manufactured in the first place, or putting really emphasis on source control. It is much more difficult, much more expensive to clean up afterwards, but source control is easy. It can be done very effectively. Now, having said that, remember that our wastewater treatment processes were never designed to remove any of these substances. So we do need to improve the level of treatment. And also there are new treatment technologies that we need to start using to be able to remove some of these emerging contaminants better. And there has been an excellent, there was an excellent discussion yesterday on national water policy. That is very important. And also remember, one water approach, if we're only talking about wastewater or stormwater or drinking water, we're not really solving the problem. To really solve the problem, one water approach is very important. So I will quickly highlight some points here, and these are results from our own research projects. And I'm not going to get into research stuff, but just to highlight the importance of these issues. Now with antibiotic resistance, so this slide is from one of my students' work, McDonald. And so what this slide shows is we basically isolated indigenous E. coli from treated wastewater, secondary wastewater before disinfection. And then we measured the resistance of these E. coli to 6 different antibiotics, including ones that are the last line of defense, that very effective antibiotics. Okay, so if we just, regular wastewater sample, random, and then what we found was 45% of E. coli in treated effluent was in fact resistant to antibiotics. And a great percentage of them is maybe only resistant to 1 or 2, but there was the 2% that was resistant to all 6 antibiotics. And so, the amount of, or the quantity of antibiotic resistance is quite significant, and this is something that should be taken seriously. The figure on the bottom, it shows the sensitivity of SARS-CoV-2 to disinfection or treatment processes that we use. And this is also very important to highlight. We are measuring, for example, SARS-CoV-2 in wastewater as a measure to maybe predict or monitor the COVID-19 case numbers. But in water, wastewater environments, SARS-CoV-2 is the easiest microorganism to inactivate compared to all other microorganisms, bacteria, viruses, protozoa, E. coli that we deal with in water and wastewater treatment. So this is not really an issue of public health safety in water environments. And I think it's also very important to convey that, because public hears about all these wastewater-based epidemiology studies, and they know that the virus is in wastewater, but it doesn't necessarily pose a threat to public health from water environments. Okay. Nanoparticles, there's a whole wide range of nanoparticles. Metallic nanoparticles are particularly important. I picked this research because what we did in this study, there are some studies, they spike very high concentrations of nanoparticles, or there's some studies that use virgin pure nanoparticles. And what we have done here is we spike nanoparticles in wastewater, which then went through anaerobic digestion, and then we land applied as a biosolids, and then looked at the impact on soil. And nanoparticles interact with other organic compounds, they transform in the environment, and they also quickly lose their toxicity. What we saw was that even in environmentally relevant concentrations, there was still some toxicity from silver nanoparticles. However, time scale is important. What we also saw, what we also observed was that the toxicity decreases over time. So, if you're looking at it like in a year, most likely the toxicity will decrease and there will not be a significant impact. And there are also long-term studies from Sweden that looked at the impact of nanoparticles on agricultural lands, for example, after sludge application. And those studies show no significant difference in the number of antimicrobial resistant genes, sorry, not antimicrobial resistant genes, but the impact from the nanoparticles. Okay, the last slide I would like to show you is about PFAS. So this is the hot persistent chemical right now, both in wastewater and in sludge. I mean, it's in the environment. It's not just the wastewater or sludge problem. It's important to realize that. However, what I would like to show here, we do not have limits yet in North America or in Canada, but there's some countries in Germany that started putting limits for these compounds. And one of my students, Erdem, what he did was he scanned the published literature and he looked at the measured concentrations in biosolid samples. And if you plot that, and now what you see here, the dashed line is 100 nanograms per gram, the German limit. And then the solid line, solid horizontal line is the UK limit. But what this figure shows is that already existing environmental concentrations are pretty high. So, I mean, there are, like if you look at heavy metal limits, for example, typically the soil or sludge concentrations are much lower than the limits. If you look at PFAS, well, already this doesn't appear to be the case. So this is going to be an issue. And PFAS, they're also known as forever chemicals. They're used in flame retardants. They're just made to resist environmental degradation. They're made to resist very, very high extreme temperatures. And this is becoming more and more important. And one of the importance of this, if you look at the US data, last year, the cost of land application sludge disposal increased by 40% in US. And the only reason for that is because many municipalities, they cannot land apply anymore because of the PFAS issue. So they have to landfill. And so there are lots of implications of this. Thank you.
Thank you very much. Let's zoom out for just a second. I want to pull back the USGS definition, Stephen, that you shared, because it was interesting to me to see, I've got it up here, that USGS at least defines contaminants of emerging concern based on what is currently monitored in the environment. And so I'm curious to get your sense in terms of how we define contaminants of emerging concern. Is a lot of this related to what is our current infrastructure to monitor and treat? Or is this more related to what are the contaminants that are out there at any given time? So I'm curious your thoughts on defining contaminants of emerging concern and by extension, identifying new contaminants of emerging concern.
Yeah, so I think it's a good question, and I think it raises some issues of clarity with respect to the origins of the particular definition and where it comes from. And so I think there's no question it would be reflective of the thinking about what is able to be monitored, and certainly from a lens as a regulator and as a scientific organization, in its space in the United States. So no question, but I think the broad way in which that definition can be applied raises the question as to the extent in which we're able to now surveil, monitor, and analyze it. That reflects the developments technologically and in laboratories, but it also goes to the heart of what's going on across the globe in other jurisdictions, and particularly in Europe, which I think in many countries in the EU and the non-EU countries in the greater European continent that who have taken significant steps to monitor and manage the waters very differently than are being done in other parts of the world. And look at France, for example, in terms of drinking water. I think they monitor somewhere in the neighborhood of like 300 different constituents in their water supply, drinking water supply. So I think it just begs the question is that it's a continued moving target. I think, and I think it's very much driven on the ability and of course the cost, but I think it's also on the role that regulators are prepared to take on with respect to their management stewardship of the water and also the engagement within their communities on water. And so I think in some parts of the world where we're beginning to see a greater degree of focus in this area is where there's tends to be a much more community oriented and sort of a descaling even in large urban centers of water management issues. and so bringing to the community, what people are valuing and looking for in terms of their water quality. And so there's demands for the kind of stringency and oversight to give confidence in the water supply as a safe and healthy and clean source of water for the particular application. So certainly for potable water, but equally so to even industries and in the agri-food sector and others who manage water within their organizations and who have to either treat or manage their water supplies internally. There's cost implications, but there's also quality issues with respect to the processes and the requirements with respect to sustainability and delivering back to the ecosystem water that's been taken out that is either as good or better than what they withdrew from. And so whether it's on nutrients or other contaminants and that are particularly important, or implementing the management tools and technologies to control those outputs and minimize impacts in the environment. So I don't know if that answers the question completely, but I think the definition is certainly wide enough to be adaptable. But I think it's a clarion call actually for a need to really be much more judicious and diligent and proactive on water-related issues. And I think as it's been demonstrated that in both Banu and my presentation, is there's a wide variety of tools that can be drawn upon to analyze and study our water supplies.
Mm-hmm. Thanks, Stephen. Banu, is there anything you wanted to add?
Right. So what I would add to that is the definition is quite fluid. Like previously, if you say emerging contaminants, that really apply to trace organic contaminants mostly. And that's what people understood. But these days, we know that there's so many different types of emerging contaminants, and they're not just from chemical origin, but also from biological, microbiological origin. And so the definition is definitely changing. And now when we say emerging contaminants, it's not only, bisphenol A or PFAS, but it's also microbiological contaminants, microplastics, nanoparticles. So all of those are emerging contaminants. It is important to be able to measure them. That is how we know if they are harmful, if they have if they have harmful effects on the aquatic environment or on public health. But that is not really a necessity either. I mean, there are thousands of chemicals. We're not measuring all of them, and there has been amazing advances both in molecular microbiology and analytical chemistry. So now we can measure these compounds in parts per billion levels. What that means is if you have $1 billion, $1 is parts per billion. Okay, so it's that amazing. And then that's that improved ability in measurement, in detection, that enables us to monitor them, to study their environmental or public health impacts. So that is really critical. And we've also seen that on the pathogen side of things now, like we didn't even know of SARS-CoV-2 a year ago, and now we have all the methods to measure them. But the ability to measure these contaminants is also important.
Mm-hmm.
I will add. I just add one more thing to this after just hearing Banu's comments, and I think it's important to put this into a Canadian context in particular. So I want to draw on the fact that we need to really think about a one water solution and thinking about the connection between our drinking and wastewater resources. And particularly if we're thinking about even recycling from wastewater into drinking water without the discharge into natural recipient waters and then withdrawing from them, that source in time. But I just think in the Canadian context, Canada is about 20% of the world's fresh water, right? Has about 20% of the world's fresh water. So it's perceived to be a very water-rich nation, right? And but in fact, but only a fraction, about 6.3% or 6.5% is renewable, right? So we consider all the fresh water that's available. We have this perception, and yet we are a country that is actually not as rich necessarily in our renewable water supply, but we have a responsibility and a stewardship and a governance around our water supply, and particularly given the unique position we are in. But I just wanted to share that because I don't think the acuity and the on that focus in Canada is as clear sometimes as it needs to be.
Now, I want to bring the conversation over to impacts, and we've got a lot of great questions in the chat. So I'm going to pull half a question that we had prepared and half a question from the chat, which is really, we've talked about some of the particular emerging contaminants of concern, so I don't think we have to dive back into that. But what are some of the risks posed by emerging contaminants to the public? And then what infrastructure do we have in place to research new impacts and risks? So essentially, how are we continuing to map the risks posed by contaminants, both to the public and to the environment as well? And Banu, do you want to start us off on that?
Okay, so it is important to recognize the type of damage or risk that is caused by each emerging contaminant is different. Depends on the chemistry, depends on the action mechanism. So, we cannot really bundle them up all under in one group. But for example, I'll give two examples, two most recent ones, like let's say PFAS and microplastics. Okay, they're very different. PFAS is of concern because they're also known as forever chemicals. They do not biodegrade. They are very persistent in the environment. But worse, they accumulate in the environment because they do not biodegrade. But worse, they also bioaccumulate in human and animal tissues. Okay, so that completely changes the conversation. And there is already research results that show that detect PFAS in blood samples in babies or in mother's milk. So these contaminants can be harmful to public. It's not just aquatic ecosystems, terrestrial ecosystems, but they can be harmful to public. Another issue with PFAS is like our treatment plants, typically they do not do a good job in removing them for obvious reasons, but it's also common to see increases in their concentrations because there are precursors in wastewater, and then these precursors, they form new PFAS compounds under different temperatures, pH. So, I mean, what happens is you end up with higher concentrations of PFAS after treatment too, so that's also a possibility. Now, microplastics, they're very different. Microplastics are also a concern. So they can, at least in aquatic terrestrial ecosystems, they can cause blockage in worms, and there's lots of research that shows the harmful effects. But also for people, plastics, we already know, many of us avoid plasticware, plastic bottles. Why is that? Because there are chemicals that leach from plastics to water. So it's not just the plastic itself, but it might be the chemicals or the resins or toxic substances that are used in making plastics. And so the type of the impact might be very different, and they may have a broad impact both on public health as well as environment.
Thanks, Banu. Stephen, did you want to add anything there?
Yeah, so I think there's a natural tendency to try to sort of bundle things. And so contrary to what Ben was saying, which I think is an important point, because I think we have to start thinking more along the lines of very, very specific and individual situations, but we do have a tendency to bundle. And so, for example, classifying a range of contaminants in terms of their hydrophobic or hydrophilic properties, for example, right, and sort of start classifying that, say they were, and on that basis. And so I think there are some differentiating features as we learn more about the chemistry, learn more about the biology. But if it was to think about just even the microbiological issues. including, just even technologies, right? So we're seeing, tremendous developments on nano-engineered iron oxide-based sorbents for separation of various water pollutants, or the growth of Legionella during COVID-19 lockdown stagnation, right, in water supplies, although not in the general public, but also confined to, let's say, large residential units or in water recirculating or water distribution systems inside the built environment. So, drawing on tools such as microbial risk assessment, in one respect, can just capture a lot of potential risk, and then the decisions that need to be made with respect to either treatment options around disinfection or boiled water advisories or otherwise, depending on where the situation might be. But the truth of the matter is, I think there are very specific issues with very specific consequences and different types of risks that pose significant consequences to the health and welfare of individuals and populations that we need to be more mindful of. And I think we need more specific solutions and more purposeful solutions. And yes, to think that we have let's say in the case of contaminants, an oxidation step in the be it ozone or ultraviolet that would eliminate many of the organic materials. I think that's I think we got to think a little bit differently about this, right? And if let alone the more problem, the broader range of issues, whether it's banning, controlling at source the use of products and so forth. But I do think that it's one that requires very purposeful and more specific understandings of the consequences and options.
So I'd love to continue our conversation over to the realm of government and thinking a little bit about the role that government can play in supporting regulation and legislation around emerging contaminants, in particular, because one of the shared challenges among emerging contaminants is that often we are discovering the impacts of contaminants before we have regulations to actually implement new wastewater treatment systems, for example. So just zooming out and tracking into what do we do about these contaminants once we have them on our radar? Banu, I'd love to hear your thoughts there.
Okay, so strong regulations are important, but the regulations also need to make sense. Okay, I mean, if you are only focusing on final concentrations or limits or ceiling limits, that's really not so useful. Of course, it is needed, but the focus should be on source control. Once these contaminants are in the environment, once these contaminants are in wastewater, there's really not so much that you can do. In a way, they're similar to heavy metals. Like heavy metals, they do not biodegrade, they're there, they do not disappear. And our best tool to minimize the impact of heavy metals is not to let them in the wastewater in the first place. So this is very similar. So there should be more focus on source control. And there are very good examples. Like if you look at Europe, they have done this quite effectively. And they, for example, have what is called REACH list. And basically that really limits the ability of companies to produce whatever chemical they come up with and use it in manufacturing. They cannot do that. They have to first show all the toxicology data, have to show that there's no environmental impact or public health impact, and then it needs to be approved and then it can be used in manufacturing. So this is very important. Like PFAS, the last 3-4 years, it's like the hot topic in Canada. But you know what, PFAS, they're being used since 1940s. Okay, in 1980s, Europe already started phasing them out. So if you have something that is out in the environment for 80 years already, it really doesn't make a whole lot of sense to try to limit the concentrations now. And imagine that there are hundreds of these new compounds. So that source control is very important. Another good thing that Europe does is what is called SIN, S-I-N list. If people want to Google, I think that's a very helpful way to help companies. It should not be punishing companies or manufacturers. It should be showing them how to do that. So what they do is they have established these lists. Some chemicals are banned, but they can also tell you, okay, these chemicals can be banned, are likely to be banned, but this is another chemical that you can use, which is not as toxic. So replacing these chemicals with non-toxic ones. And so that is a very useful exercise. And this is also what should happen, that you should also help the industry to come up with cleaner, greener alternatives. And they need guidance in this.
Really interesting to look at that burden of proof, right? And shifting from a reactive approach to a proactive one. Stephen?
So a couple of things come to mind. One is, I think, the relationship between effluent guidelines and standards set by the federal government and those that are managed at the provincial level. And I think, there is some disconnect in some instances in some elements. And I think about, let's say, disinfection byproducts, right, for which there are guidelines and standards at the federal level, but that for which we know are often exceeded in different parts of the country, as an illustration of a contaminant. So I want to frame it that way as well. And so to me, this is really about stewardship and governance and the role of science and the evidence-based research that needs to really be a strong guide and also to be consistent across how we address our water quality issues. I think the second is also taking a very strong orientation to one water solutions and thinking about more of a distributed model with respect to our water operations to help to, I think, manage more effectively, and also the opportunity to throw greater pathways for innovation for managing our water supply, which could have an impact on how we treat and protect our water resources. And protect human health in this respect. And so we're seeing much of that shift in other parts of the world, but we haven't seen a wholesale shift in Canada with respect to the factors that. So it's a systematic approach to this. It's just not handing government and policy. It's a systematic approach to our stewardship and management of our water resources, right from the community level through a national framework in particular. And that's particularly important to consider. So to me, those are the things that come to mind.
I'd love to pick up on what you mentioned there, Stephen, around pathways to innovation. And there's a couple questions in the chat around what is the role of new technologies, or how effective are new technologies? Often this comes back to our challenge of contaminants of emerging concern, or a range of contaminants requiring different technologies. But I'm curious to get your perspective on, do we have effective innovation pathways in place to treat contaminants of emerging concern in Canada, or is there something we could be doing better?
Oh, I think absolutely. I think if you look at the population across the academy in terms of research and focus in water, from University of Calgary, Aqua, to of course the work at Carleton, Ryerson Urban Water, you can get at University of Waterloo. Our stewardship, at least in the context of an academic enterprise, I think of the status of our innovation coming out of companies. I look at the history of our membrane technologies and where that began in Hamilton, to our stewardship and leadership in UV disinfection and treatment options and just on UV technology. There's many illustrations and developments and innovation and the potential. I would say we tend to focus, our markets are what they are, and so we have to think about our global positioning on this. There are emerging companies like Pani Energy out of Victoria, in terms of their applications of AI and data and the power of data in terms of efficiency and operations of water infrastructure, including desalination, of course, and not something of a major issue in Canada, but nonetheless important in terms of a worldwide contribution to innovation. So there's no shortage, in my view, of innovation in water in this country. And I certainly saw that in technologies that came out of Queens when I was there, and relationships with international global multinationals like Veolia and others. So Canada is certainly a source of phenomenal opportunity. I think we have tended to go outside of Canada to commercialize, to innovate, and to translate. We've not been really early adopters of our own technology, and one of the major bottlenecks, as I see it, is government in terms of really the room to permit and allow technologies to be implemented. Rather, it's hard to change legislation and change policy, and most things are done through special permissions, and it's just not a very productive and effective way to translate technology. It's easier to migrate into EPA territory to get approvals on your technology, and you can be struggling for years after sorting it out in Canada. That's been my experience with a number of whether it's technology in microbial detection systems, molecular sciences. We've seen companies like Lumen Ultra, for example, that increasingly playing a big part in microbial detection, molecular detection, but really grew out of the water side of the business and so forth. But I don't think we've made it easy for innovation and technologies to be commercialized in this country. We're supportive of it in one regard. On the other hand, I think government has to figure out a way to make it easier, and notwithstanding the due diligence and the expectations and requirements around claims and oversight. But I just think that companies are prepared to do that, but we make them go through unusual hoops and put huge barriers in front of our companies and technologies to be implemented effectively in this country.
Thanks, Stephen. Banu?
Excellent comments on the innovation side of things, Stephen. Stephen is also in this. He's the VP research, so he's very familiar with innovation in the Canadian universities, and also we have very successful Canadian water companies. Where we're lacking, okay, so this needs to be said, is unfortunately we're not investing in our water and wastewater infrastructure, like at the treatment plant level. So we have these technologies, innovation, we have the capability, but if you visit our wastewater treatment plants, and I mean, they play a key role now in removing these contaminants. They are very well operated. It's not the shortage of knowledge or anything, but look at the processes, they are rather basic, and unfortunately we do not have these technologies yet at our own wastewater treatment plants. I mean, what we have, I'll tell you, like activated sludge, it's more than 100 years old. Okay, the technology itself, it was really designed to remove organic carbon, not even nutrients. And nutrients came later, but when we look at nutrient removal in Canada, a majority of it is maybe chemical phosphorus removal and extended aeration for ammonia. Okay, so we need to invest more, especially in processes like advanced oxidation processes that can really oxidize these chemicals or kill these pathogens. And that is something that we need to do better. And that's directly related to funding.
So this might be our last question. Maybe we'll squeeze in two. We'll see how we do for time. But we've got a really nicely positively framed question from the audience, which is there anything that you're excited about in the next year or two, either as federal initiatives or for yourselves as research initiatives that are really advancing the conversation on emerging contaminants? Stephen, go ahead and start us off.
Yeah, so I will say, and sadly on one hand, and I don't mean to bring a negative to this question, but it's actually turned into be so positive. And I would just go to the point on surveillance, right, and the response to COV-2 in particular, right. We've seen a remarkable pivot, but an ability that actually our university responded to government and when called upon to step in and assist, right, and we're able to do so quite. I think it says something about the investments made in university, the value, value investment in the complement of young people who are drawn to our labs to have further experiences of moving their careers forward and their future. And I think that says something about our talent and our ability to develop talent, but also to give back to society in a meaningful way. And so to me, that was a very powerful outcome in terms of the collaborative spirit and the ability to take advantage of this. But it also revealed the huge capacity and opportunity to think about how we might be innovative and innovating collaboratively going forward. So I'd like to highlight that. I think in more ways than one, the clarion call for change in terms of sustainability, clean tech, and so forth. I think as we think to a post-pandemic recovery and a world that we all want for the next generations that will follow, I think speaks well to that future if we really want to do this seriously. I think sadly, with respect to just the consequences of what has been transpiring related to in our Indigenous peoples and communities, and highlighting further, lack of addressing the issues, but the opportunity to move forward in charting a path if we're really fully committed to the type of future we hope for, realizing the capacity and the skills and the abilities we have to work together. I think there's a tremendous opportunity for a future and for Canada to be really at the front edge of this. But it's up to everybody, and it's up to certainly our governments for sure. But I tend to take an optimistic view, and why spend time educating and training the next generation if you weren't optimistic? So there you go.
It's interesting how in the water space, just as in many other spaces, COVID has been this very strong coordinating and accelerating force, and to see the level of collaboration around the wastewater surveillance work has been really phenomenal.
Yeah, partnerships and collaborations. I think going forward, our solutions for the future, regardless of what we're doing and what we propose to do, is going to have to be, we're going to have to be much more collaborative, deepen and strengthen our partnerships. I think this is critical to our future.
Banu, is there anything you wanted to add there?
Right, so I am excited about the Canada Water Agency. I'm really looking forward to that. I think that's very much needed. And one recent development, I think that became very clear during COVID-19 is we're finally breaking silos. And it used to be like, wastewater people are in one silo, drinking water people are in one silo, and then the companies, they never interact with academics, government doesn't really interact with academics. And now what wastewater-based epidemiology for COVID-19 did is it really brought together all these players, and they're effectively working together, they're collaborating. And I know lots of people who never worked in wastewater, now they're doing all these tests in wastewater. So there's also more acceptance finally, okay? And then wastewater is in fact a very powerful tool. It's like the fingerprint of a society. It's not just, COVID-19, but it's all kinds of chemicals, drugs, illegal drugs, like we can measure anything, and there are lots of opportunities. And now we do have the support of provincial governments, federal government, and industrial sector as well. So I'm really looking forward to this unified approach in working together, breaking down the silos.
I think we're going to wrap it up there, but that's such a great note to finish on. And Stephen, I appreciate you bringing the conversation back to our initial First Nations challenge focus as well, because that level of urgency and coordination is really what we need to advance that conversation. So I appreciate everyone joining us. We've had so many great questions in the chat. And so these questions will be answered on an ongoing basis. They will stay in the chat. And so the speakers will have an opportunity to come back and answer some of those. So don't feel like your questions, if they haven't been answered through the session, won't be answered. But otherwise, there's a lot coming up today, including the keynote with Charles Fishman in 15 minutes, which gives you a chance to grab a coffee and refresh and then come back and rejoin us. And after that, Banu will be moderating a virtual meetup in the community board. And so that's a great opportunity to continue the conversation here. But I do want to say thank you so much to our two speakers for joining us. I think we could have gone for 3 hours with this session, but I really appreciated the opportunity to chat both about the research around emerging contaminants and also around the role of regulation and collaboration in moving us forward. And for the audience members, if you have any questions, feel free to message me as well through the platform, and always happy to continue the conversation. Thank you all. Enjoy your break, and we'll see you in 15 minutes.
Thank you.
Thank you, Alan. Thank you, Banu.
Thank you. Thanks, everyone.